Welcome back, section 3.2. Here we go. There's a lot in this section. So we started off by interpreting slope and y-intercept. Then we talked about what this least squares regression line is, the dangers of extrapolation, talked about residuals, residual plots, what that helps us to determine. How do you interpret the standard deviation of the residuals? What is this r squared? How things are influenced by outliers. So let's just get into it here. You have a regression line. Okay, y hat is the predicted y value. You have a y-intercept and a slope. So we were very detailed in how we interpreted the slope and the y-intercept. The y-intercept is the predicted value of y when x equals 0. You have to have that word predicted in there. For the slope, it's the predicted change when x increases by 1 unit. So it's the predicted change in y as x increases by 1 unit. And we'll take a look at a specific example here. So the context here is all these trucks, how many miles are on them, and what's the price that they sold. So you can see your least squares regression line equation here. So this y-intercept would mean we would predict that a car with 0 miles driven, a brand new car, or in this case truck, would have a sale price of $38,257. The predicted slope would be, as the number of miles driven increases by 1, we predict the price will decrease by $0.1629. Right? So that word predicted, we can't guarantee it's going to happen. All right. As far as making predictions go, in order to make a prediction, you just have to substitute into the least squares regression line equation. So here, if I have a car, or in this case, a truck that has 100,000 miles on it, and I want to predict how much it's going to sell for, plug in 100,000 into the equation. I'm going to get a dollar amount out, almost $22,000. That's going to be my predicted amount. All right. Then we moved on to this idea of extrapolation. And extrapolation, remember, means when you're making predictions outside of the range of data you have. So here we have trucks from 0 to 160,000 miles on it. So if I have a truck with 300,000 miles on it, I should not be using this equation to make a prediction about the price because I don't have any data at 300,000 miles. That's called extrapolation. Whether you're going past the data you have or before, obviously I can't have negative miles driven, but anything outside of the interval of values for the x variable, if you're trying to make predictions on that, that's extrapolation. That's dangerous. This is probably not going to be a good fit. All right, residuals. Residuals are the vertical distance between the point and the line. That's the vertical distance. Remember, the points are the actual. The line is the predicted. So for residuals, we looked at kind of two formulas. Residual equals actual minus predicted. R equals A minus P. Residual equals actual minus predicted. Or sometimes the residual is referred to as the error equals the Y value minus the Y predicted, which is the actual minus the predicted. Okay? You can have positive residuals, negative residuals, a residual of 0. Okay. So if I want the residual for this one truck that had this many miles and a price of this, well, first I have to get the predicted price. This is the actual price of the truck. So I substitute the number of miles driven, I get this value. That's how much I predict it would sell for, but it actually sold for this $21,994. So I take that actual minus the predicted. This residual is negative about $4,800. What does that mean? You have to be able to interpret this. It means the actual price of the truck was about $4,800 less than the predicted price, sale price. All right, so it's finding residuals and then interpreting them. Least squares regression line, what does that mean? Least squares means if we take every single data point and draw on the residual, that vertical distance, so say that distance was 10, and then I create a square, so 10 times 10, the area of that square is 100, and I did that for every single one of the data points. What the least squares residual line is doing is it's minimizing the sum of those squared residuals. That's why it's called least squares. One thing to know about the least squares regression line, it has to pass through the mean point, which we call x bar, y bar. It has to pass through that mean point. Let's see what else we got. Okay, that's an activity. Moving on. Oh, you can use the residual plot to determine if a linear model is appropriate. So a residual plot is just created when you take the scatter plot and shift it so that the least squares regression line is horizontal. So all that's happening between here and here, all I'm doing is turning this so it's horizontal, and then I'm looking at the distance from that least squares regression line, positive or negative, how many. So this blue line here, make sure you understand, is the least squares regression line. What we want to see is random scatter. We don't want to see a pattern. If we don't see a pattern in the residual plot, that tells us we have an appropriate linear model. If you do have a pattern in the residual plot, then that tells us a linear model is not appropriate. So here's the scatter plot, here's the corresponding residual plot, big pattern, big issue. You can see this is not a linear form. So using a linear model would not be appropriate. All right. So here, not patterned. That's random scatter in the residual plot. Therefore, a linear model would be appropriate. All right. It talks about how to do a residual plot on the calculator. Then we jumped into this idea of how well does the line fit the data. So we're going to look at S, which is the standard deviation of the residuals, and this thing called R squared. Well, S is the standard deviation of the residuals. So standard deviation is just the average distance from the mean. So this is going to be standard deviation of the residuals. So this is going to be the average distance between the actual and predicted values. We want to have a smaller standard deviation, more precise estimates. That's ideal. Depends on the context, but that's what we would want. That would mean it's a better fit. Then we got into R squared. Let me clarify something. R is your correlation coefficient. C-O-E-F. Okay, I think I got that spelled right. And R squared is literally just the correlation squared. That's all it is. It's called the coefficient of determination. Coefficient of determination. So it's a fancy term. All it is the correlation squared, and we usually express it as a percentage. And R squared just measures this. R squared is what percent of the variation in the y variable, whatever that is accounted for by the linear model. So if we're talking about that question with the truck miles driven and price, say R squared was 80%. That means 80% of the variability in the price is accounted for by the miles driven. That means there's another 20% of the variability in price that is due to like what else? Like how well the car was kept up, how many owners there have been, like the if there's dents, stuff like that. There's other variables besides miles driven that obviously are going to influence the cost as well. So higher R squared value, better fit for the data. So then you have to be able to look at a scatter plot. Residual plot, is the linear model appropriate, yes or no? And then both calculate and interpret the value of S and R squared. Well, you don't have to calculate the value of S. That's going to be given to you in a computer output. We did quite a bit of stuff with this. Just refreshing your memory on the computer output. The column that says coefficient, those are going to be your values for the slope and the y-intercept. Whatever one goes with the constant That's your y-intercept. And the variable that's in the computer output, that's your explanatory variable, so your x variable. And the number in front of x is your slope. So you have to be able to look at a computer output and write the least squares regression line. And you have to be able to find s and r squared. R squared adjusted, we're never going to use that, so you can ignore that. So something like this, here's a computer output. There's r squared, there's s. That's your y-intercept, the 103. There's your slope, 2.74. That's your explanatory variable, foot length, and somewhere in the problem they would have had to tell me